Hello, I'm Paul Beckwith. I'm with the University of Ottawa Laboratory for Paleoclimatology. And this is my website, paulbeckwith.net. I try to do posts on this site at least once a week. Sometimes I slip a little bit, like lately. Usually I like to post new videos every 2 or 3 days, but again, it's been more or less every week recently. So when I go into these, sometimes you just need to back off a bit and think about things, big picture, take a break from your your usual routines. So when I disappear for a while off the web, you can probably find me on this website called Lichess, L-I Chess, just under my name. It's one of my passions, maybe call it an addiction. And these are a couple books that feed it. Now this is interesting. I'm going to make a link to climate change. This is Improve Your Chess Pattern Recognition, Key Moves and Motifs, and More Key Moves and Motifs. Excellent books by New in Chess. So pattern recognition. Chess is all about pattern recognition. The better you become at chess, the less of the board you'll have to look at. They've done psychological studies following people's eye movements playing chess, and the beginner will scan over the entire board equally. As you get better and better, your eyes will sort of scan to key parts of the board because you recognize the patterns. You recognize a clump of pieces here, a clump of pieces here, maybe a certain theme, and so you actually get a better feel or understanding. And this is what I also try to do in climate change. You look at the overall picture, you look at how all the pieces are changing, and you try to figure out where things are heading, how quickly, to allow you to make projections and to kind of understand the overall climate system joining the dots. Not enough scientists have done this. This is starting to happen more and more often as climate disruption gets worse and worse. So in this particular video, a series of videos. I'm going to do a series of videos for you, and I'm going to really drill down and look at methane, because methane is considered like the smoking gun of the climate. In terms of global warming potential, the methane molecule averaged over a 100-year time scale, the number you always see about methane causing warming compared to CO2 it used to be 24 times, something like that. The number on a 100-year time scale is 34 times. So one methane molecule will cause 34 times more warming so it's on a per molecule basis than CO2. Now, the methane lifetime is only about a decade or so. Why do they always pick that 100-year time scale? That's ridiculous. So on a 20-year time scale, the global warming potential, if you like, of methane is 86 times. And on a few-year time scale, so it's coming up in the Arctic, on a few-year time scale, if it was to stay there, which it doesn't, the air circulates around, but it can take a while to leave the Arctic, it's more like 150, 200 times. So methane is a very, very powerful greenhouse gas, as you know if you're watching my videos. If you're new to my videos, then this might be new information for you. So I'm going to look at all of the characteristics of methane. So this report here, if you go to the AMAP site, okay, then there's a document called All on Methane. Okay, it's the AMAP Assessment 2015. Methane is an Arctic climate forcer. It would be nice to see an updated AMAP assessment on methane to see how things have changed. But this document is very, very good for explaining all the nuances of methane. So you can go to this site, you can download the document, and I've got it here. Okay, so AMAP Assessment 2015, methane is an Arctic climate forcer. This is an ecologist on an Alaskan lake. So he's got a plastic catch assembly. He puts a hole in the ice. He's got this plastic sheet which goes in, and the gas methane bubbles up from there's methane coming up as the lake is warming because of climate change, global warming. Methane is bubbling up. It's captured by the plastic. extracted, and the concentrations can be measured, and the ebullition rates, the rates that the bubbles are being formed, can be estimated. Then if you can extrapolate over the entire lake, you can kind of get an idea as to how much methane is coming up from this situation. Okay, so let's go into this document. So like I say, you can read this. So my job here is to give you the highlights of this article, the key parts. So first of all, this is the first of a series of videos, like I said. So I'll give you a bit of background on methane, Arctic warming, Arctic temperature amplification in the past, and what's expected in the future, what's happening now. Okay, as way of an intro, 2 times is the number that is thrown out there. The Arctic is warming twice as fast. If you go to the high Arctic, it's more like 5 to 8 times. There's lots of different definitions of the Arctic. Do you consider it north of 60? Do you consider it north of the Arctic Circle? Do you consider it the 0 degree isotherm, annual isotherm? So if the annual yearly temperature is 0 degrees, that could that delineate the Arctic? The tree line, freezing degree days. There's many different ways, so people define the Arctic differently. But if you consider over most of these ways, the warming is at least 3 times faster. And then as you go higher up, it's much, much faster than the global average. And what's really important is the rate compared to the equator, and the equator is warming slightly less than the global average. So it's the difference between the temperature in the Arctic and in the equator that determines the jet streams. And that temperature difference is decreasing because the Arctic is warming much faster than the equator, and therefore the jet streams are slowing and becoming wavier and causing all those extreme weather events. So I'll always try to bring this back to the big picture to join the dots on the overall climate system and how it's changing. So we can talk about a global methane budget and the role of methane in climate forcing in this chapter. So there's obviously natural sources, and there's anthropogenic or human-caused sources. So this is an overview of the sources, and so those sources put methane into the atmosphere, ocean system. Okay, now there's also methane sinks. So the overview, well, basically it's hydroxide. The hydroxide radical, OH minus. So take a hydrogen off water, you have OH minus. There's mediation by methane. There's nitrous oxide involved. We'll go into the reactions, the photochemical reactions. So you have photons from the sun, energy from the sun, breaking apart molecules which react with other molecules, etc. And this basically, the hydroxyl radical is very reactive, doesn't last long in that form, OH minus. It reacts with molecules that are there, and it's the main scavenger in the atmosphere, if you like. It's the main molecule which removes pollutants and breaks down molecules in the atmosphere. So we'll look at how it does it and the long-term changes in this molecule. And also there's local changes. So the hydroxyl, for example, underneath a cloud will be much, much lower than the hydroxyl that is in a sunlit area, because there's photochemical reactions going on to produce the hydroxyl. In areas where there's very little water vapor, like in the Arctic, for example, it's colder. Cold air can only hold much, much less water vapor than warm air, so therefore there's much less source for the OH minus to be formed. Therefore, there's much less OH minus hydroxyl in the Arctic. Therefore, methane that is in the Arctic, for example, will have a lifetime much longer than 10 years if it was to stay there. Okay, because then now you have to look at how the air is transported, how the air circulation is occurring. And this is looking at the radiative forcing, which I've already alluded to, global warming potential of methane. Okay, now in this chapter, it's all about the natural terrestrial methane sources. So terrestrial, land-based. So what are the sources of methane on land? How do we measure them? what do we set up? I mean, we can do on-the-ground measurements. We can put up towers and do something called eddy covariance studies to get an idea as to methane. New techniques are using laser spectrometers. We can capture flasks of the air and monitor them with gas chromatographs, etc. Okay, so we also have satellite measurements, and we can calibrate the satellites based on the ground measurements. So where is the methane coming from? Well, we've got soils in the Arctic, which have carbon from decayed organic matter, and when the carbon's broken down in the absence of oxygen, which is anaerobic decomposition, you get methane produced. When there's oxygen available, you get CO2 produced. Okay, there's vast amounts of permafrost. There's in Siberia, in northern Canada, Alaska. So how much methane can we expect as those sources are warming, as the permafrost is thawing? Then the organic material can be attacked. As long as it's frozen and below zero, the bacteria can't break it down. But when it thaws and it's swampy, etc., then you'll get lots of methane produced. Okay, so and so there's the natural sources, but the natural sources are changing. Okay, now there's also marine sources. So we're focusing on the Arctic here. So what are the marine sources? There's subsurface methane production. Okay, so there's permafrost that was above sea level before the ocean. So the oceans were lower by about 120, 130 meters at the peak of the last ice age, 21,000 years ago, because so much of the water from the ocean was removed and it was stored as ice on glaciers on land. And so the sea levels were 130 meters lower. You could have organic material growing on the surface, and then it gets colder and the stuff freezes to permafrost and the sea level rises. So we have the permafrost on shallow continental shelves, just so the top parts would have thawed, but it still depends on the water temperature as to how much thawing there is, as how much is still frozen. So you have all this organic material on the sea floor and the continental shelves. You also have these gas hydrate formations, okay, where the pressure is high, temperature is low. Methane is in these gas hydrates, which is basically a lattice of frozen water surrounding methane molecules. So when these thaw out, there's an expansion of about 160 times, and if it's under the surface, that can build up pressure and cause these blowholes like in Siberia. There's also methane in the water. So methane is exchanged with the atmosphere, and there's a certain solubility in the water. The colder the water, it can hold more methane within the water. As the water is warming up, the methane comes out of the water. So there's surface water sources of methane, both in fresh water and in salt water. So this talks about the aerobic. There's also bacteria that can consume methane, both anaerobically and aerobically. So you have methane bubbles coming up from the seafloor. Does the methane reach the atmosphere? If the water's shallow, then most of it does. And if it's coming up very fast, then it can saturate the consumers of it, the anaerobic and aerobic consumers of it in the water, so more of it will reach the surface. So it depends on the rate of the bubbles coming up, also the depth of the water. How do we measure it? Okay, and how much is there coming from the Arctic Ocean? How much has come up in the past? What about the hydrates? How much is going to come up? And so on. Okay, so we're talking about that here. And now this chapter talks all about anthropogenic methane sources. So when we bring up fossil fuels from deep in the ground, the pressure is relaxed. The methane comes out of there's lots of methane that comes out of oil that is brought up. Methane is basically natural gas, so fracking and things. So how much methane is there? How do we measure it? Long-term, short-term? So this is on a daily basis, on a monthly basis. How do we determine where it's coming from? Okay, and when we can model where it's coming from, where it's going to, and see how the climate responds to methane. So all of these details, so the methane monster, the clathrate gun, etc. I'm going to talk about all the details of methane in the next number of videos. So thanks for listening.